lesson for today is going to be a beginning to thinking about hypothesis testing. And so let's talk a little bit about the assumptions for least squares. So if all you want to do is estimate the parameters beta, you actually don't have to make any distributional assumptions for epsilon. And this might be a little bit counter to what you've learned previously, but the reason that we have distributional assumptions is so that we can create confidence intervals and do hypothesis testing. So if you want to create confidence intervals or do hypothesis testing, those distributional assumptions are really important. So since we're doing least squares, we assume that the errors are independent and identically distributed with a mean of 0 and a variance of sigma squared. So those are assumptions that underpin least squares. Because we'd like to do hypothesis testing and create some confidence intervals, we assume that distribution, so we say that the errors are identically distributed, and we assume that the way that they are distributed is normal. And so we can write it like this: the errors are normally distributed with a mean of 0 and a variance of sigma squared. And so since y equals x beta plus epsilon, we then know that y is distributed as normal x beta with a variance of sigma squared. And so from this it follows that beta hat, which is equal to x transpose x inverse x transpose y, is going to be distributed as normal with a mean of beta and a variance of x transpose x inverse times sigma squared. Okay, so hypothesis testing. So we're just going to talk about one small piece of hypothesis testing here, but we're going to build on this as we go on. So often we want to compare a small model to a larger one. And parsimony is really important. And what I mean by parsimony is we want to fit the smallest model that can best explain our outcome. But we need to find a way to determine if the small model is good enough. So we can compare the residual sum of squares for two models to do this. And so if that residual sum of squares for the small model minus the residual sum of squares for the larger model, if that difference is small, then the fit for the small model is almost as good as that for the large one. And so the test statistic of interest here is going to be the residual squared of the small minus the residual squared of the large divided by the residual squared of the larger. So we're going to scale this by the larger one. So how do we decide what value is good enough? So the residual squared of the small minus the residual squared of the large divided by the residual squared of the larger. This is that statistic that we sort of come up with as something sensible to do because we want to compare our small model to our larger one. And maybe we would determine it as good enough if it's greater than some constant. So now we have to pick a constant to use. So what we've done, you've probably seen this in previous classes, is we can actually turn this statistic into an F statistic by transforming it just slightly, and then we can compare it to the F distribution to pick the constant that we'd like. So the F statistic is going to look very similar to what we had laid out, but we're just going to divide by the degrees of freedom here. And so the numerator of the F statistic is the residual sum of squares for the small model minus that of the large model, divided by the degrees of freedom for the small model minus the degrees of freedom for the larger model. And then, so that's the numerator. And then the denominator is going to be the residual sum of squared for the larger model divided by the degrees of freedom of the larger model. And so if the small model has 3 variables and the larger model has 5 variables, what do you think the degrees of freedom are for each of these? So the small is going to be n minus 4 because it's going to be n minus p plus 1. And so in this case, p is 3. There are 3 variables and then 1 for the intercept, so n minus 4. And the large model is going to have n minus 6 degrees of freedom. So 5 plus 1, 6. And then we'll compare this to an F statistic from the F distribution. So we can find an F value from the F distribution by looking at the F distribution and finding the constant that exists when we have the first parameter of this F distribution is going to be the numerator degrees of freedom. So that's the degrees of freedom of the small model minus that of the large model. And then the second parameter is going to be the degrees of freedom of the larger model, the denominator degrees of freedom. And so we reject the null hypothesis, which is that the small model is equal to the large model, if the F value from this F statistic that we get is larger than the F value from our F distribution at some alpha level, where alpha is usually something like 0.05. So what if you want to compare your full model to an intercept-only model? And this is what we're going to be doing in the application exercise in this last part. So we've got H naught, our null hypothesis, is that beta 1 equals beta 2. It's equal to beta 3 all the way up to beta p, and all of those are equal to 0. So the null hypothesis is that all of the beta coefficients, with the exception of the intercept, are equal to 0. And so what would the residual sum of squares for that small model or that intercept-only model be? It's just going to be the total sum of squares. And so we end up with the total sum of squares minus the residual sum of squares divided by p, that whole quantity divided by the residual sum of squares divided by n minus p plus 1. And so what I want you to do is I want you to calculate this F statistic for the model that we fit in the lab. And so the full layout is, you'll see it in the application exercise, but if you recall from the lab, we fit a model where we were predicting salary based on the number of times at bat plus the number of hits. And so what I want you to do is fit that model, and then I want you to compare it to an intercept-only model and calculate the F statistic. And then see if you can find where in the linear model's output you see that value. It might be in the summary function, just as a hint.